Hi, and welcome to Spotigraph.
The main idea for this project was to connect artists on Spotify in some way. We first chose to connect the artists based on albums that they have worked on together. Since the Spotify API is accessible to anyone who has an account, we would be able to make calls to that API and get our data that way. Our initial plan was to create something in real time so that if it would constantly ping the API to grab information about artists and albums.
So what is Spotigraph? Here's a little bit about what our final product is able to do. So we use a Python script that we generated to create CSV data that contains songs from the Spotify database, including features like song titles, lengths, artist names, and their Spotify artist IDs. And then we load that CSV data into a graph implementation that we created where songs are edges and artists are vertices. The main feature of our program is finding the shortest path or a landmark path between two artists based on songs that they've collaborated on, with edge weights being set to song duration. We can also print a list of all the artists loaded into that graph, and we can run and print out a breadth-first search traversal of artists in that graph starting from an input root artist. So for development through fall break, one of our team members tried to use the curl library through C++ to make requests for the Spotify API. This was very new territory, especially with making web requests with a lower level language. However, after checking in with the professor, we realized that we could not follow our initial plan of only making requests to the API and instead creating a static object like a CSV or JSON file so that the TAs and CAs could properly test our code. This also meant that we would have to create an actual graph implementation. Spotify's data when requesting an album did not include all the artists that worked on the album, only the main artist. So instead, we switched our edges to represent songs that the two artists have collaborated on together. This required a lot more processing on creating the CSV. So we used a Python script to create the CSV, and we ran into some problems with parsing it later. Since artists can use commas or double quotations, some formatting issues had to be dealt with before parsing the data with our C++ code.
Our data is organized in a CSV file where each line represents an edge that contains two artists connected by a song that they have collaborated on. We chose to include both the artist ID and the artist name so that we could use these in our hash map to create an O1 lookup time for artists given IDs. We chose to include the song ID so that in the future, if we would want to interact with a user and create playlists for them, they would need the Spotify song ID to get that song from the API. We also included the song length in milliseconds to create a weight for our graph. This would later be used in development for Dijkstra's algorithm.
With the development in C++, we created a CSV parser that turned our CSV that was generated by our Python script into a graph. There were some difficulties with escape characters like commas or double quotation marks, but that was changed within the Python script so that parsing could be done easily. We decided to use the adjacency list graph implementation because of its ease of use in accessing an edge given a vertex and vice versa. As well, it has multiple O1 lookups that could greatly increase our performance when doing our searches.
Our adjacency list graph implementation holds songs as edges, holding information such as a song's name and Spotify ID, as well as a pair of two artists featured on that song. Edges also held the song's total length, which is used as the weight in the shortest path algorithms. The vertices are artists, with each vertex containing a list of pointers to all adjacent edges. We deliberated for a while on which graph implementation to use between edge list and adjacency list, but ended up going with the adjacency list because of O1 lookup times for accessing adjacent edges to a vertex. To keep things simple, we omitted functions to delete vertices and edges, which were not needed in running shortest path algorithms. To test the graph implementation, we made a small CSV file, loaded it into a graph, and printed out all artists and songs in that graph to ensure it matched our expected output. We also tested it implicitly with tests for Dijkstra's and shortest path, which depend on our graph implementation to work.
In inserting vertices and edges, we needed an efficient way to check for duplicates. We landed on using an unordered map to store our vertices in our graph class, where the key was the artist ID and the value was a pointer to an instance of our vertex class. Since the unordered map was stored in a hash table, we could check for existing vertices by calling the map's find function with O1 lookup time, searching based on the ID of the artist. Edges were a bit trickier to find duplicates for, since each edge holds 2 artists to represent a collaboration, and those could be in any order. Our CSV data could list the same song many times for each combination of 2 artists listed on it. So for instance, if we had a song with 3 artists, we could permutate that to artist 1, artist 2, artist 2, artist 3, and artist 2 and artist 1, etc. So we had to avoid inserting duplicates of the same edge. The adjacency list implementation really helped out here, as each vertex knew what edges it contained. So we made a helper function to check if an edge exists by passing in 2 vertices and the song ID of that edge. So we got all the edges of the first artist, and then we checked it against all the edges of the second artist to see if there's an edge, aka song, with both artists and the same song ID. This was much faster than looping through the entire list of edges stored in an edge list implementation that we had in our graph class.
Our traversal implementation uses breadth first search to print out a complete list of all vertices sorted by distance from one specific artist. Compared to depth first search, this implementation better suits the goals of our program by traversing the graph starting from lowest to highest degree instead of individual paths from the root to a leaf node. To test the traversal, a smaller graph was made and traversed by hand. This expected result was later compared to the results of the traversal for validity. One of the biggest problems with the traversal was calling the function based on an artist's name. Because the start of the traversal depends on the artist's index in an unordered map of vertices, a ON lookup is required to convert the artist's name to its respective vertex, then to an integer by finding the index of the vertex within an unordered map. Another challenge faced with the traversal was verifying that all vertices were visited only once. To account for this, a check between the sizes of the return list and the unordered map of vertices was done to ensure no more or less artists are accounted for.
We wanted to create a shortest path algorithm to create the shortest playlist in terms of listening time between 2 artists. We chose to use Dijkstra's algorithm because our songs cannot have a negative song length. To do this, and to test this, we created a short CSV file that we applied Dijkstra's algorithm to by hand. Then we tested the code by comparing the paths output by the computer and the paths we found doing the traversal by hand. Since we had spent time developing a curl method that could not actually work for the final project, we were actually quite behind on the mid-project check-in and only had half of our graph implementation done. We decided to code Dijkstra's in parallel with the graph implementation and assumed that the functions needed for Dijkstra's worked in the graph implementation, even if they had not been coded yet. This was uncomfortable but necessary given our time restraints. After our graph implementation was done, we could fully test Dijkstra's algorithm. We decided to use Dijkstra's algorithm as our shortest path algorithm for a landmark path. Our goal for this project was to see how crazy artist connections could be, going from someone like Ariana Grande to Jacob Collier to John Bellion. Testing to this algorithm was much easier since we already had Dijkstra's testing material. All we had to do was compare our landmark path to 2 separate Dijkstra algorithm calls, which is very similar to the definition of our landmark path.
In order to use all of these algorithms and the graph implementation, we enabled CLI by writing code in the main file. We also created the Spotigraph executable that must be called in order to run this program. As you can see here, we have an example of a call using the CLI. At the beginning is the executable, followed by a source artist, a destination artist, a file path to a CSV file with information from the Spotify API, then a flag which specifies the path type, which in this situation is Dijkstra's. The CLI will be formatted differently for each algorithm, but this one is just the Dijkstra's. And after this command is ran, you will see the output below. What happens here is that the shortest path will be printed to the console containing the names of the songs and the collaborators linking each artist. In this example, Ariana Grande is linked to John Bellion through the song Heartstroke, Big Dripper, and then Good Things Fall Apart. We are very pleased with our progress as we have implemented all algorithms and created a very interesting product to explore musical tastes by creating links between artists. As well, we have a command line interface to interact with our program. In the future, we would like to develop a way to access the API directly instead of having a static CSV file for our data. This way we can access all artists on Spotify. Our project management and team building were very up to par as each person communicated well within our text group chat and took responsibilities both in coding and the write-up, such as documentation or this presentation. Overall, we are very proud of our product and hope that you enjoy using it and find something interesting. Thank you.